we all know what we're talking about. So, some titration definitions. The analyte is whichever of the two compounds. So, we have a known and an unknown, and then we have an analyte and a titrant. Those are not necessarily, there's no sort of definite pairs there. And so the analyte is, oops, let me get my pen. The analyte is the species being analyzed right? This is not necessarily the unknown. This is whatever is in our receiving flask. And so maybe we need some glassware terms as well. Titration usually has a burette. And then we've got our little Erlenmeyer buddy. And so in here is our analyte. Sometimes the analyte is the unknown, sometimes it's not. But the analyte is whatever we are analyzing. And so this is the receiving flask. This is the burette. And then, of course, this is our titrant. And so the titrant is whatever species is being dispensed, right? From the burette. So analyte and titrant, a lot of times when we talk about analytes, it's our unknown, but not always, especially not in titrations. Okay? Equivalence point, you know this. The equivalent point is when there are an equivalent number of moles of analyte and titrant. Okay. That's a very Gen-Chem kind of answer, and it's hard to rectify that explanation with what about a diprotic? There's only 1 mole of this diprotic acid, but I need 2 moles of base. That's not equivalent. And so a better definition of this is that the correct number of moles to react in whatever the stoichiometric ratio is, right? And so I'm going to put a couple of dashes there and go moles required to react completely. And that sort of takes into account any kind of diprotic activity that we have, either in an acid or a base. All right, now our indicator is a compound with some physical property. Very often, I would say more than 95% of the time, that physical property is a color change, but it doesn't have to be. The indicator has a compound with a physical property sorry for my slant here, that changes when the reaction is at or near completion. Perhaps the most famous indicator, of course, phenolphthalein. Phenolphthalein has a color change that is at about a pH of 7.7. Right? We use it for strong acid, strong base titration because 7 and 7.7 are pretty close to each other. We'll talk a little bit more about that as we discuss acid base in general. But the indicator should be at or pretty close to our equivalence point. Now, equivalence point and endpoint, these two get confused a good bit. They are not the same thing. The endpoint is whatever point at which the pH, the indicator changes color. So it's sort of our signal that the reaction is over. This is why we want an indicator that has a color change that's near the equivalence point, so that we don't see the color change and then have to keep going for, add another 5 milliliters or something. We don't want that to happen. All right, these last two might be new terms for us. A blank titration, of course, is very similar to having a blank in a UV vis experiment. Hopefully, you're somewhat familiar with that. But generally speaking, it's sort of like a control, right? We want to make sure that as we do the titration, if we're using DI water, maybe its pH is not exactly 7, and so some of our base has to react with carbonic acid that's dissolved in the water to make it neutral. And we want to know how much base that requires, right? Maybe our indicator requires a tiny, tiny bit of base in order to do that color change. And we want to know how much that requires, especially in an analytical situation. And so the blank titration helps us to reduce any error between the endpoint and the equivalence point, right? We're trying to reduce the error in between those two as much as we can, but it also takes into account sort of as many of the other variables as we can handle. And so this is a titration done without the analyte. Okay, say that it takes 0.21 milliliters for plain water and a drop or two of phenolphthalein to go from colorless to magenta, right? Just a super tiny amount. Well, if that's the case, then that's how much base is necessary to neutralize our water and to affect a change in our indicator. And so we're going to subtract out that 0.21 milliliters from all of our future volumes, because we know that 0.21 didn't really react with our analyte. It reacted with everything else in the solution. And so that's important to do, again, especially if we care about being very accurate, very precise. All right, a back titration is a technique where you over titrate, you add excess titrant, on purpose, not by accident, right? And then you go in and you use a standardized solution to go back to the endpoint. Right? And so if we've added excess titrant, right, this is past the end point. So we're going to make instead of our phenolphthalein being just a pale lilac purple like we like to see it. Our phenolphthalein is deep magenta, and we're going to titrate it back to where it's colorless. This could be done for a couple of reasons. Maybe you're titrating a very weak acid, and that weak acid does not have a very sharp endpoint at all, right? And that equivalence point is the sharpness of an equivalence point, we'll talk about this a little bit later, has to do with the strength of the acid. And so as the acid gets weak, and as weak as water, right, so a Ka of 10 to the negative 7 or something like that, then the equivalence point is not very sharp. It's not easy to differentiate between the equivalence point pH and pHs around it. Whereas with a strong acid, strong base, you go from a pH of, pH of 4 to a pH of 10 within a drop or two of your titrant. And so that's a very sharp, very clear, very quick endpoint, equivalence point. Not always the case with a weak acid or a weak base. And so, if you're titrating a weak acid with a strong base, you're going to go past, add too much base, and then go back with a strong base, titrate it back so that you can actually see that endpoint, and you can actually be confident that you're sort of hitting it exactly where it needs to be. Okay, so back titration, a technique that's sometimes useful, especially if we have a unclear endpoint. So I'll just put here, helps provide a clear endpoint. All right, so like I said, hopefully some of these terms are familiar with you, bringing some memories of 124 back. Some of these things may be a little new though. So in doing acid-base titrations, we always look at a titration curve, sorry, not calibration curve, a titration curve. And I'm going to do one that's acid versus base. So strong acid, strong base. And our titration curves are always pH versus volume of titrant. And so we're measuring if we have a strong acid as our analyte, we're going to have a curve that goes like this, a very sharp equivalence point, and then it sort of goes up like that. And so in a titration curve like this, we're really interested in 4 data points. Okay. So let me put those in a different color here. Oops. We're interested in 4 points. We're interested in this very initial point. We're interested in some point in here between the initial and the equivalence point. And then we want to be able to calculate a pH after that equivalence point. And so these 4 points, really there's only 2 points and then 2 regions, right? So I'm going to label this A, and this B, but really it's anywhere in here. Could be B. This is C, and then past our equivalence point, right? All of that is D, because the calculations are the same at any volume there. So when our volume of titrant is 0, so point A, there's no titrant added. And so the pH is just equal to the pH of the acid solution. Okay. Now, again, because I'm doing an acid-base reaction here, I'm saying the pH of the acid solution. If you had started with a base, it'd just be the pH of the base solution, right? And so that's easy enough to do because it's a strong acid. pH is equal to negative log concentration. I'm just going to abbreviate strong acid as SA. Okay. Now at point B, we are neutralizing some of our acid little by little, but we haven't neutralized all of it yet. And so at this point, we are reacting away some of our acid. Neutralized, maybe that's a better word to use. And so we need to essentially subtract the amount of base that we've added from the amount of acid that we started with. Now, there's a couple of things to take into consideration here. The first is when we look at the concentration, we can't really subtract concentrations. We can only subtract moles. Right? The other thing is we want to make sure that we take into account the fact that our overall volume has increased. Right? We started with whatever volume A had to begin with, and then we've added some base as we go along the line there. And so there are a couple ways of doing this, but I'm going to write it out this way. The concentration of our strong acid is equal to the concentration of our strong acid that we started with, so let me put 0 down there, times the volume of the strong acid, minus the concentration of our strong base, times the volume of the base. Now, remember, it's concentration times volume, so that we're subtracting moles. But then we have to get a concentration back out, and so we divide by the volume, which is the volume of the acid plus the volume of the base. So again, just to point it out, we subtract the moles, and we divide by volume to get concentration. Now, this is again a little bit of a shortcut. You know, you could do a limiting reactant kind of table. You may not know what a limiting reactant table is, depending on who you had for 124. But it looks a lot like an ice table. You just use up something completely. And so you're welcome to do that here. But this is how my brain works. So the moles of the acid, I'm going to subtract out the moles of the base that I've added to it. And then I need to find the concentration of the leftover moles of acid, so I divide by the total volume at that point. Okay. All right. So, point C is the easy point, because for a strong acid, strong base, for a strong acid, strong base, at point C, what's our pH? Who's got it?
7.
Hey. So for a strong acid, strong base, the equivalence point is always going to give us a neutral solution. Right? Again, also, if you'll notice, the titration curve is almost a vertical line around that equivalence point. And that's why it's okay to use an indicator that has a pH, an endpoint at a pH of 7.7, like phenolphthalein, because the amount of volume necessary to go from 7 to 7.7 is much less than one drop of our titrant. And so we're not going to introduce a whole lot of error because of the size of that difference. Now, if the pH change happened at a pH of 9 or something, we'd have to add several more drops to go from pH of 7 to pH of 9, and we would introduce a lot more error that way. Okay. All right. And so this last point, point D, we have reacted away all of our strong acid, and so now this is just a solution of strong base. With a couple of caveats, we can't just take the volume that we've added and find the new concentration because based on the volume difference, because we've reacted some of that away with our strong acid. And so point D and point B look very similar. Right? For point D, we just switch acid and base. The concentration of our strong base is equal to the concentration of our strong base to begin with times the volume of the strong base minus the concentration of the strong acid that we began with times the volume of the strong acid divided by the total volume at this point. And so again, it's moles of base that we started with minus the moles of acid that we reacted away. So that's the leftover moles of strong base divided by the total volume at that point, just to convert those moles to concentration. So strong acid, strong base is the easiest one. It's very easy to switch this over to if strong base is your analyte and the strong acid is your titrant, right? If we were to do it that way, let me just choose another color here. Right? If we were to do it that way, we'd end up with a curve that looks something like this. Strong base as my analyte. And so it's pretty easy to work out how those equations would change if you start with a base instead of with an acid. All right. Any questions about strong acid, strong base kind of titrations? All right. So moving on to weak acid, weak base. This one gets a little bit trickier. And I'm only going to talk for now about monoprotic. So a monoprotic weak acid with a strong base. Remember our weak acid, we abbreviate as HA. And so that's going to be HA, strong base still SB. Right? And so this doesn't look too different versus pH. The main difference is that that vertical region is much shorter. It's not quite as abrupt. It's not quite as sharp as you see in the strong acid, strong base. However, we still just have those four different regions, those four different types of calculations that we want to take into account. A, then region B, then our equivalence point C, and then this past equivalence point region D. Okay. All right. So at point A, right, the only thing we have in solution is HA. And, in chapter 6 and 9, we talked a lot about how to find the pH of solutions of a weak acid, right? We know how to do that. And so we know to use Ka equals x squared over F minus X to find concentration of H plus. Okay, we did those kind of calculations in the equilibrium review, but we also did those kind of calculations in chapter 6. We did a couple of those problems. All right. Now, to talk about point B, I'm just going to write up here a generic reaction. For my strong base, I'm going to use NaOH. And this is going to react to form NaA plus water. Right? And so because all of these ratios are 1-to-1, because it's a monoprotic weak acid, and I'm using a strong base, it turns out that the amount of strong base that I add is equal to the amount of weak base that is formed, right? So here's our strong base, here's our weak base. It's a 1-to-1 ratio. For every mole of strong base that I add, I'm forming 1 mole of weak conjugate base. And so in point B here, we are converting our weak acid into its conjugate base. And that happens completely at point C, at our equivalence point, right? We go from 100% HA to 100% A minus, but in between, we've got a mixture of those two things. What do we have? And we have a mixture of a weak acid and its conjugate base.
Buffer?
Yeah, we've got a buffer. Right? And so this B region is our buffer region. And so we know that pH equals pKa plus log of base over acid. Now, base over acid, how do we calculate that? Given what we have here. And it's based a little bit on what I just told you. The moles of the strong base that we add equal the moles of the weak base that are formed. And so the moles of the weak base are the concentration of the strong base times the volume of the strong base at that point. We divide this by the moles of acid that are left. Well, the moles of acid left are the moles of acid we started with minus the moles of base. And so this is the concentration of our weak acid, HA, times the volume of HA, minus however much strong base we've added that has reacted with our weak acid. So again, this is just base. Actually, I need to take my brackets off because I haven't done base, concentration of base, have I? I've done the moles of base divided by the moles of acid. If we're talking about the same solution, acid and base have to have the same volume. And so the number of liters cancels when we divide, right? If they're both in, say, 475 milliliters, then the top one is the moles of base divided by 0.475 liters. The acid is moles of acid divided by 0.475 liters. And the volume cancels out. And so even though we tend to write it as concentrations, it is A-OK for us to write it in terms of moles. And so this is the same as moles of acid, moles of base over moles of acid. Okay. And that works at any point in region B, any point between our initial data point and our equivalence point. Okay. So at point A, I said that we were HA only. What are we at point C?
Don't you have a little bit of the weak base?
You better have a whole lot of the weak base at point C. Yeah. So I'm at point C, I'm done with my weak acid. There's no more weak acid left. I've converted all of those moles of weak acid into moles of weak base. And I don't have any strong base left over because I've used it all to react with my weak acid. And so the only thing that's in solution is the weak base and then the counter ion to my strong acid, my strong base, which of course doesn't do much. Sodium floating around doesn't do a whole lot for us. And so the only thing left is A minus. Again, we talked about how to find the concentration of, the pH of a solution of a weak base. We know how to do this. We need to find Kb, and we're going to use x squared over f minus x to find not OH minus, not H plus. Now at point C, at this equivalence point, we need to be careful about how we calculate this formality. What is it the concentration of? Right? Because we have to take into account the fact that the concentration of the weak base is different than the concentration of the weak acid at point A. Right? And so the F here, let me call it not F. How about that? I'm going to erase this F. I'm going to erase this F. I'm going to erase this F. So over here in my acid, I'm going to put concentration of HA. Here I'm going to put concentration of A minus. And so that concentration of A minus is equal to the moles of HA, which is the initial concentration of HA times the initial volume of the acid divided by, now we're not adding or removing any moles, right? The moles of every molecule of HA became a molecule of A minus. And so we're not changing any moles here. We're just changing volume. So it's the volume of the acid plus whatever volume of the base that we've added to it. And so your concentration of A minus better not equal the concentration of HA that you used in at point A. Now at point D, all we have left is strong base. This is very similar to the strong acid, strong base situation. Right? After the equivalence point, all we had left was strong base. And so this point D is exactly the same as point D in the previous slide, where the all we have to do is find out the concentration of OH minus, the concentration of our strong base, okay, equals the concentration of OH minus equals the number of moles of base that we have, which is the concentration original of the strong base times the volume minus the concentration of the acid. Oops, I put an S instead of an H. Concentration of the acid times the volume of the weak acid divided by my new volume. And so that point looks exactly like the point D in the previous slide. I don't know. Some things got erased there. Okay. Now again, going from monoprotic weak acid with a strong base to a monoprotic weak base and a strong acid isn't too tricky. We just have to flip some things around. If you have any questions about that over the weekend, do reach out. I'm happy to answer any of those questions. There is one other thing that I want to talk about, and I'll sort of give you a hint about this diprotic stuff. For a diprotic weak acid, that's H2A. Here's our curve with the volume of our titrant and the pH. We're going to have two equivalence points, one for the first proton coming off, one for the second proton coming off. One of the big assumptions that we make is that the protons come off in that stepwise fashion. That's a pretty good approximation. It's unlikely that if you've got some extra base hanging out, that he's going to take off the second hydrogen, which is harder to pull off than the first hydrogen. And so it's likely that you'll have, you'll pull the first hydrogen off of all of those diprotic acids. And then once, if you have enough base left over, you'll start pulling off the second hydrogen. And so you end up with a graph that looks like this. We have a first equivalence point, and a second equivalence point, and then it goes off. And so now we've got several data points that we can look at. We've got A. We're going to label this one B1, and label this one C1. B2, C2, and D. Right? We know how to solve A, right? We know how to do buffers. Buffer 1 is going to be between H2A and HA minus. Oops. I don't know what's the matter with my eraser, but he erases everything he wants. Okay, there's A. B1 is H2A and HA minus. B2 is HA minus and A2 minus. D is just exactly the same. At C2, so at C1, we have only HA minus, and at point C2, we have only A2 minus. A2 minus is easy to deal with. He's a weak base only. We can do KB and solve him just like we solved point C in the previous slide. When we have HA minus though, and it's just HA minus, he's equally as likely to pull a proton off of water and go back to H2A as he is to give a proton to water and go to A2 minus. He can sort of get torn either way. We have a term for that, if you recall. We call it amphiprotic. There's also amphoteric. These are a little bit interchangeable. Amphoteric. But he can behave as both an acid and a base. And that makes calculations really tricky. How do you do an ice table if at the same time he's behaving as a base and as an acid? Well, when we talk about chapter 10 and diprotic stuff, we'll talk a little bit more about that. But for now, at point C1, because he's going both directions, he sort of pulled both directions, and the pH at point C1 is equal to the average of the two pKa's. And so you end up with a pH that's pretty easy to calculate at C1 because it's halfway between pKa1 and pKa2. All right, now region B1 and B2, those are both buffer regions, right? And there's a special data point, not only in diprotics, but in monoprotic weak acids as well. There's this special data point that's right in the middle. It's half the volume of the equivalence point, and we call this the half equivalence point. Not a very creative name. And at the half equivalence point, what do we have in region B? What is our solution made of?
I want to say
Yeah, so pick one, B1 or B2, either point, pick one.
H2A and HA minus.
Yeah, and if we're exactly in the middle, what's the concentration of those two? How are they related?
Same.
Yeah, exactly. So at these half equivalence points, the concentration of, I'll just say H2A is equal to the concentration of HA minus. We had a special thing when we did the Henderson-Hasselbalch equation, if you remember. When the concentration of base is equal to the concentration of the acid, what's special about the pH?
Equal to the pKa.
That's right. And so since you did this one, I'm going to say pH is equal to pKa1 because this is all for this data point down here. For this half equivalence point here, right, it would be the concentration of HA minus equals the concentration of A2 minus, and pH is pKa2. So there are some easy data points to fill out along that titration curve, even though it seems a bit daunting at first. Okay. All right. Well, that's an excellent stopping point before we get into precipitation titrations. And so I'm going to leave it there. Like I said, that worksheet is uploaded to Moodle. It's in the problem set part of our class webpage. It's 5 problems: strong acid, weak base, strong acid, strong base, strong base, strong acid, weak acid, strong base, weak base, strong acid, and then this a diprotic weak acid with a strong base, just like this one. And so, do your best. Go ahead and work as much through that as you can. Bring any questions you have on Monday. I'm happy to answer those before we finish up this chapter on titrations Monday in class. All right?
Dr. Davis,
Yes.
I actually already have a question about it. I looked at it and I'm like, it says calculate pH like 5 milliliters before and after equivalence point.
Yeah.
So do you have to calculate the equivalence point first?
You do.
Okay. Because I'm used to it just saying like added 5 milliliters of like strong base or strong acid.
Yeah.
Wow.
So you will have to add the calculate the equivalence point. I tried to be nice. All 5 of the problems have exactly the same concentration with exactly the same volumes. So, the equivalence point should be the same volume in every titration. It's just about doing the math, not about making you do extra.
Okay, got it.
All right. Well, feel free to hang around if you've got some more questions. If not, have a great weekend. And I really hope that I see you in person on Monday, but I'm not crossing my fingers.
Thank you.